Now let us discuss performance considerations of in-order pipelines and motivate the discussion towards out-of-order pipelines. So let us come to the basic question. If I ask you, is computer A faster than computer B, what are you going to say? So many people give wrong answers. They say higher frequency, that's one wrong answer. They say more memory, another wrong answer. Any combination thereof, another wrong answer, right? So people, given whom this question is asked, the the answers can be different flavors of wrong, but the answers are seldom correct. So what does it mean for computer A to be faster than computer B or processor A to be faster than processor B? Well, short answer, nothing. So performance is always with respect to a given program, right? So what you do is that, so I'm kind of, referring to the processor as a computer because there are other aspects as well, like the memory, the hard disk, and so on. But, even if you can isolate the processor, well and good, or if you want to consider everything in unison, well, that's also fine. So in any case, let's take the two substrates A and B, where A and B can be individual processors or entire machines with memory and hard disk, doesn't matter. So what I would do is that I would run the same program on A and I would run the same program on B. And I'll simply measure the wall clock time, which is the time with a standard clock, right? With a wall clock. And on whichever system it runs faster, I say that that system is faster, right, with respect to that program. Now let's say, for example, it's a chess program. Then if, let's say, computer A is faster than computer B, I say that, well, for chess, A is faster than B. So now let's say if I want to remove memory and hard disk, well, you can always ask me, how will I run a program without involving the memory and disk? Well, if my program is small enough, we will define what it means to be small. But let's say that it doesn't use memory and disk that much. Then, and if it's predominantly limited to the CPU and its resources, we can say that CPU A is faster than CPU B, right? So we can see, we will see in the later chapters how do we explicitly ensure this, but essentially whatever the system constitutes, we just run the same program at both places, sit with a stopwatch, wherever it runs faster, we say that, look, that system is faster. So of course you can say that, but then, you can always counter argue with me. And you can say that I say a supercomputer is faster than a mobile phone. Well, how is that? Well, that is true if I can say with reasonable certainty that give me any program on computer A, it will run faster than computer B, right? You write any program that you want and I can show you that A will always be faster than B, then I can make a general statement that A is faster than B. In general, I cannot make that because, especially among alternatives where it's not very clear, like, I give you one laptop with a 2 gigahertz processor, another laptop with a 3 gigahertz processor. What is again 2 gigahertz and 3 gigahertz? It is the clock speed. The clock speed that we have been discussing, right, is just the clock speed. So in that case, it's not very clear. See, the distinction between a supercomputer and a mobile phone is very clear, right? One is very large and very expensive and very powerful, right? And the other is small and cheap, right? So the difference between these two is rather stark and it's kind of clear. But if, let's say, I give you a faster laptop and, laptop of one kind and a laptop of another kind, in that case, it is not that clear. So then you say performance is with respect to one program. It can also be a set of programs. So what I can do is that I can take 5 programs, right? So let's say run them. So let's say I can get T1A, T. So where T1A is the time that program 1 takes on system A. So what I can actually do is that I can sort of run them at both places and compute these times. How do I compare the times? Well, one is that I can take the arithmetic mean, but that would make little sense because let's say that one program's baseline running time is 1 second and then for the other it's 1 hour. That will kind of skew the results. So what people normally do is they take a geometric mean, right, of the ratios. So typically whenever you consider a ratio, you take a geometric mean in computer architecture. So what you do is you do this. You compute a ratio, all right, and then you take the geometric mean of the ratios, and then you can say that look, for this suite of programs, a suite is a set of programs, computer A is 10% or 15 or 20% faster than computer B. All right, so now let us take a look at the performance equation, which is arguably one of the most popular and most famous equations in computer architecture. So we have essentially defined performance to be some quantity as the time that a program takes. So let us do a little bit of dimensional analysis. If I have number of programs by number of seconds, so then I can add a few extra variables. So I can have, of course, programs over here, instructions, they will cancel out, cycles and cycles, number of cycles, number of cycles. Hash stands for number of and number of seconds. So what you will see is that this essentially comes down, if I consider a single program, as a number of instructions per program, right? Roughly on an average, number of instructions per program, which for a single program is actually the number of instructions. And note, these are not static instructions. These are actually dynamic instructions, which means that, so consider a loop. In the body of the loop, if there are 5 instructions, then there are 5 static instructions, but if the loop runs 100 times, there are 500 dynamic instructions. Alright. So the number of instructions here actually points to dynamic instructions. The number of instructions per cycle is known as the IPC. So this is an inherent property of the design, the architecture of the processor. Is very important. We'll take a look. And the number of cycles per second, well, that we know, that's the frequency, right? So number of clock cycles per second is the frequency. So assuming just a single program, which we will assume for the better half of this chapter, the performance, the performance, I will say, is a quantity that is, so it depends on the source. So many sources would define this quantity to the performance. We will not do that. And so throughout the book, what we will do is that we will say that performance, well, in some cases, for simplicity, we'll consider this to be a proxy of performance. But in general, we will say performance is IPC times frequency divided by number of instructions. This is what we will say in general, right? And we assume the constant of proportionality is kind of the same for all programs, right? For all processors that we are comparing. So the IPC, so you need to remember these terms. We will be using these terms throughout this chapter, throughout this book, and that too very liberally. The IPC is the number of instructions per cycle, and IPC is 1 divided by the CPI. Well, CPI is the cycles per instruction, alright. So IPC and CPI initially a lot of students confuse. So it is important for you to know that in IPC, I comes first, I stands for instruction. IPC is instructions per cycle. CPI is cycles per instruction. One is the reciprocal of the other. Frequency we know, number of instructions we know. And as I said, in some cases, we will loosely refer to performance as equal to this quantity. And in some cases, we will say it is proportional. It doesn't matter. Performance, it's a relative number most of the time. So the constant of proportionality will cancel. but the most important is the interplay of the IPC, the frequency and the number of instructions. That is the most important thing that we need to consider, and their relative interplay. So what does the performance depend on? Three things, as we have said: number of instructions, frequency, IPC. Number of instructions, how do we reduce it? Because if we reduce it, our performance will improve, it will increase. Well, that depends on the programmer. It depends on the logic. So the logic requires a lot of instructions, or it has a lot of code that doesn't do anything. That's a bad idea. It also depends on the compiler. So often we will have a lot of code that is not really very optimal. All right, and that has a lot of instructions which are known as dead code, don't really do much or don't really do anything. So most compilers are supposed to remove them. All right. So that's where a smart compiler can definitely reduce the number of instructions. Let's look at frequency and IPC. Wherever you see this burger sign, well, it's good. One is that go and eat a burger, so it will give you some energy to understand the rest. The other is, it is not just real food, but it's intellectual food. It is intellectual food for thought. So that should give you an additional impetus to think. So frequency is a rather complicated thing. Okay, it's kind of crucial to our entire discussion. So it depends on the transistor technology. Well, of course it does, because the faster the transistors, higher we can crank up the frequency. But it also depends on the architecture, and this is the most interesting aspect of the connection between the frequency and the architecture. Architecture in this case is a pipeline. So given a fixed transistor technology, let's say the total amount of work that we need to do, which we can quantify in terms of time, let this be T. For a given instruction, let the worst case time be T, which is essentially the total time that it takes to process an instruction. So don't care about pipelining, it's just end to end. So this is known as the algorithmic work, which is the total amount of work that needs to be done by the CPU. So the maximum of this for processing an instruction. So what we do is, if we have a k stage pipeline, then essentially we do T by k units of work, measured in terms of time, of course, per stage. In addition, the stage will have a latch delay, which we can say delta, because every stage, right, has some logic and then it has a pipeline latch. So we can say it is T by k plus delta. So if we assume that the pipeline stages are balanced, which means that all the stages have roughly the same time, right? Balanced actually means they have exactly the same time. Then in this case, each stage takes T by k plus delta units of time. So the minimum clock period that we can, so what did we say? We said that, look, what happens is that at every negative edge, data comes from this side to this side via a pipeline register. For the entire duration of the cycle, it keeps getting processed. Then when the clock cycle ends at the next negative edge, it enters the second latch. So this is the clock period. So the clock period, the minimum clock period is equal to T by k plus delta, which means that the maximum frequency F max is 1 divided by T by k plus delta. All right. So this is a very, 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 very important piece of understanding, that as we increase the number of pipeline stages, what happens? As we increase the number of pipeline stages, so let us say that k tends to infinity. In this case, this factor will become 0 and the clock period will be equal to the latch delay. So which clearly says that, look, beyond a certain point, there is no advantage whatsoever in increasing the number of pipeline stages. Don't do it, because you'll be limited by the latch delay. So you can't increase the frequency further. However, that is a lot of stages. When you are talking of 3, 4, 5, 6, 7 stages, there is a definite advantage in increasing the number of pipeline stages. Hence, keep doing it. As you see, the maximum frequency at which you can run the processor will keep increasing. And if let's say T by K is much greater than delta, then what you essentially say is F max is proportional to K, right? This is easy to work out, right? If delta is much lower than this, then F max is approximately proportional to the number of stages, which means as I increase the number of stages, I can keep on cranking up the clock frequency, right? That's very important. If I don't do that, I have no advantage of pipelining. The only advantage of pipelining, as we will see, is that so what happens if I increase the number of stages, each stage becomes smaller. The smaller a stage, lower is the clock period, smaller is the clock period. Hence, higher is the frequency that can be supported. So to increase the frequency, what do we need to do? Well, we simply increase the number of pipeline stages. The converse is also true. If we can increase the number of pipeline stages, we can also give ourselves a higher frequency. So note that whether we actually crank up the frequency or not, that depends on other factors, but clearly increasing the number of pipeline stages allows us, so the key word is allows us, right, makes it possible to increase the frequency, right? Whether we do it or not, we will see, but at least we can do it. And given the fact that the performance is proportional to the frequency, what you can clearly see is that, look, as I pipeline more, I can increase the frequency and my frequency will increase the performance, because the performance equation, as we just saw, is IPC times frequency divided by number of instructions. Number of instructions beyond a certain point we have no control, because the compiler technologies have become reasonably mature. They are not getting better in this regard, at least. So pipelining, if we can do more of it, we can afford ourselves a higher frequency, which is good. And the last is IPC. So IPC is again a complicated beast, which is dependent on the architecture and the compiler. Well, why the architecture? Well, one, we saw a great example of increasing IPC. How did we see that? Well, we introduced forwarding. So forwarding effectively reduced the number of stall cycles, which reduced the wasted work, which increased the number of useful instructions we can process per cycle. So that increased the IPC. So how can the compiler help increase the IPC? Well, it can rearrange the code in such a way that we lose as few cycles as possible to data hazards and control hazards. So in that case, lower the number of stall cycles, lower the CPI and higher the IPC. So a large part of this book is devoted to this aspect of how to increase the IPC. And as we have seen, the IPC and frequency are also rather connected. So we will explore these aspects in the next few slides, how they are connected. But at least what do we know up till now? We know that, look, the number of stages in a pipeline is definitely connected with the frequency. How? By this relationship over here, that when the number of stages, when T by K is much larger than the latch delay, the maximum possible frequency is roughly proportional to the number of stages. So if I go from one stage, which is a single cycle processor, to a 5-stage pipelined processor, I can increase my frequency by 5 times roughly. And IPC, as we said, as we have more of these tricks, like forwarding was one such trick, we can increase IPC. Similarly, consider a load use hazard. So in load use hazard, we have a load, then we need to have a stall, and then we have the use. So the stall is a wasted cycle which reduces IPC. So what a smart compiler can do is, it can have a load, it can have another instruction, let's say an add instruction, which is of course not dependent on either of them. Even if it is dependent on the load, we can still get the value via forwarding path. sorry, I take that back. It is not dependent on the load, okay? So this can only be a store for it to get the value. So let's assume it's an instruction that is independent of the load, right? It's an independent instruction. So I'll put an I over here to signal independence. So then, well, I can have the use over here. There are no stall cycles and my IPC remains high. All right. So a host of tricks give us a high IPC. So what have we seen? We have seen, look, there are three factors: IPC, instructions, and frequency. Instructions are wholly dependent on the compiler and the programmer. The frequency on the transistor technology, right? Faster transistors, faster frequency. So let me call it transistor tech. Sorry. And also the number of pipeline stages, right? And what is IPC dependent on? Well, the IPC is dependent on, of course, the rate of stalls. It is dependent on the rate of stalls, how many stalls. It is dependent on compiler technology of how the code is rearranged to avoid stalls. And of course, tricks like forwarding and so on. That also increases IPC. All right. So what is the IPC of an in-order pipeline that we saw? Well, if it's a perfect pipeline without any stalls, right? And so consider a 5-stage in-order pipeline that we saw, and we can see instructions coming out. There is an observer sitting over here. So the observer will pretty much see one instruction coming out every cycle. Why not? After all, there are no stalls, right? So this will happen. And if this does happen, then in the ideal case, the IPC will be 1. However, we'll have stalls. So the observer might see a valid instruction. After that, it might see a stall cycle, maybe one more stall cycle, then a valid instruction. So then, so let's look at these 4. So we have 4 instructions out of, sorry, we have 4 slots, right? We have 4 cycles. Out of them, there are only 2 valid instructions. The rest 2 are stalls. So the IPC is equal to 2 by 4, which is 0.5. And why did this happen? Because we had stalls. So the IPC in a pipeline processor is always less than 1. All right. So where are we now? The IPC of a pipeline processor, we know for sure, because of stalls, is less than 1. Of course, the IPC in a single cycle processor was higher. It was 1, but we'll come to that later. And the methods to increase IPC are, well, of course, forwarding, great. Having more not taken branches in the code, well, this reduces the number of control hazards, great. Sometimes your instruction and data memories can be slow. They can take multiple cycles to return the value. Those multiple cycles will be counted as stall cycles. So having faster instruction and data memories also increases the IPC. All right, so that's the third mechanism. All right, so given that, now let's take a slightly deeper look. So as I said, frequency is 1 by clock period, and each pipeline stage is expected to take 1 clock cycle. That's the way it is architected. So every pipeline stage, the way it is architected is that you have a pipeline latch, you have a large piece of logic, can be an adder, multiplier, divider, doesn't matter. So at the negative edge of the clock cycle, the data is visible to the logic. The logic, you do whatever computation you want, and by the end of the cycle, right, by the end of the current cycle, so maybe like this, again the data is here, such that at the beginning of the next cycle, the data is visible here. Reducing the clock period, well, use faster transistors or use more pipeline stages. Are there limits to increasing frequency? Well, yes, there are. Even if I have a large pipeline, nevertheless there are. Can we increase the frequency to 100 gigahertz? Well, the answer is no. Why is the answer no? The reasons are, keep these facts in mind. So we will see this in chapter number 11 on the chapter on power and temperature, that the power roughly in modern processors is proportional to the cube of the frequency, right? So power is proportional to F cube. So if I double the frequency, my power will increase 8 times. So as it is, our laptops and desktops consume a lot of power. A typical laptop might be consuming somewhere between 20 and 50 watts, maybe 100, a few. And a desktop would happily consume around 250 watts. So if I make it 8 times, that will be 2 kilowatts. That's roughly the amount of power that an air conditioner uses. That will be too much. Another result from thermodynamics, the change in temperature, delta T, is proportional to the applied power, roughly. Which means that the increase in temperature, as it is, chips are very hot. So while you are playing a game, the die temperature can be as high as 100 degrees C. So if this increases further, essentially the whole chip will melt. Additionally, to support a large frequency, we need a very large number of pipeline stages that will create a large number of hazards, extremely complicated and expensive forwarding logic with a very large number of forwarding multiplexers and a large amount of logic to figure out which multiplexer to run when and where. So because of that, there are also design reasons of not having many pipeline stages. And of course, power is the biggest limiter of frequency. This is probably why in the last 10 or 15 years, as of 2020, the frequency has not increased. Alright, so how many pipeline stages can we have? Well, there is another argument. Assume you can still dip your processors in liquid nitrogen and somehow cool them, right? And assume you're the best designers in the world who give you fantastic forwarding circuitry. We are still limited by the latch delay. So as you can see, in this case, if you have few stages, per stage there is a large amount of logic, so the latch delay is somewhat limited. With a larger number of stages, they become roughly equal. And if I have a lot of pipeline stages, essentially the entire delay of the stage is dominated by the latch delay. Now that we have spoken about the frequency, it is now the turn of IPC. So IPC and CPI will be two terms that we'll be using heavily. The CPI is defined as 1 over IPC. So typically the CPI is used while doing mathematical calculations with regards to the performance of a pipeline, and an IPC is more like a high level quantity that is either measured or is used for doing more high level decisions on deciding which kind of architecture is better for a given program and so on. So it doesn't matter, they are still similar quantities, one is the reciprocal of the other. So the CPI can simply be defined as CPI ideal, which is the ideal CPI assuming no stalls, plus the stall rate, the number of stalls per instruction, and the stall penalty, which is the number of cycles per stall. Alright. So both of this, if we see the number of cycles per stall and the number of stalls per instruction, so stalls will cancel out. And the final unit will be number of cycles per instruction for this quantity as well. So this can be reasoned out rather simply, that for any observer sitting outside, if there are no stalls, it will see the ideal CPI. So the ideal CPI, if you are not considering other sources of cycle loss, then it is 1, and also it will see some stall cycles, and the number of stall cycles per instruction is the stall rate times the stall penalty. So the stall rate will remain more or less constant. It can be intuitively reasoned. It has also been seen in experiments. So it will remain more or less constant per instruction with the number of pipeline stages, in the sense that, well, this does tend to increase those slightly as the number of pipeline stages becomes high. But we can say that's the reason we have used the word more or less, that the stall rate would remain similar, but the stall penalty will increase, which basically means that in terms of cycles, the stall penalty will increase. And this can be seen very easily over here, that if you have a very long pipeline, then we'll also have these large dependencies, right? Not just between stages, but between any two instructions. And we thus have to make an instruction wait for a reasonably long time or a longer time as compared to a simple 5-stage pipeline. Hence, the stall penalty as we increase the number of stages, right? There are a lot of stages. It is possible that an instruction here might have to wait for 2 or 3 cycles till it can get its data. So the stall penalty will increase. So this will, which means that this quantity over here, the number of stall cycles or the stall cycles per instruction, this is this quantity. The number of stall cycles per instruction, this quantity over here, this quantity will increase. All right. And given the fact that this quantity will increase, this will lead to a net increase in CPI. And a net increase in CPI is equivalent to a net loss in IPC. So this is an important learning that we have over here, that as the number of pipeline stages increases, the IPC will actually go down, right, in our in-order pipeline. And it's not a generic statement, but in our in-order pipeline, as the number of stages increases, the IPC will go down because the number of stall cycles is increasing. All right, so this is an important point to keep in mind, very important point to keep in mind, that the IPC will start with a good value of 1, and with an increasing number of stages, it will just keep going down and down and down. So summary, why we cannot increase frequency by increasing the number of pipeline stages? Well, power and temperature are by far the most important and the most compelling arguments, that the power is proportional to a cube of the frequency and the temperature is proportional, so roughly proportional to the power linearly. So the power as is too much, the temperature as is too much, cannot be increased further. There is the effect of the latch delay, in the sense that if we have longer pipelines, the latch delay will dominate the clock period. Furthermore, the stall penalties as measured as the number of stall cycles per instruction will also increase. And so whatever gains we get by increasing frequency will kind of get negated by reduction in IPC, and also the complexity of designing the forwarding logic, the interlocks, and verifying the whole thing, that will become very complicated. So since we cannot increase frequency, what do? We increase IPC, right? So increasing frequency, as we just saw, is fraught with problems. So instead, it is a much better idea to actually increase IPC. So what is it that we can do? Well, a simple idea is that, look, don't issue. So what is issue? So issue basically means send an instruction to an execution unit. So at the moment in our pipeline, what is called as the issue width, the number of instructions we issue per cycle, that is 1. So let us increase it. So let us have a wide pipeline where we fetch multiple instructions together, 2, 4 or 8. We decode multiple together, and we also issue to execution units multiple together, multiple instructions, right? So this is known as a superscalar processor. A superscalar processor pretty much can execute multiple instructions per cycle, right? So this is where, so there is a built-in instruction level parallelism that it exploits, and it executes multiple instructions per cycle. So what we can do is one way of creating an in-order superscalar processor, which was similar to the original Intel Pentium idea, which incidentally was a very revolutionary chip designed in the early 90s. So that used to have two parallel in-order pipelines called a U pipe and a V pipe. So in this case, we can have multiple in-order pipelines. All right. So we can have multiple in-order pipelines over here, and these in-order pipelines, as you can see, each one of them will have 5 stages, and they will just fetch instructions, run them in parallel. If there are no dependencies, no hazards, then well, we have an IPC improvement, which the IPC at the most can go up to 3, which is great, which is 3 times 1. What's the problem? There are a lot of problems. So the problems will come when there are dependencies between instructions. Dependencies between instructions will always be there. So there is no way that we can actually get rid of it. And if we have an n issue processor, we can have dependencies between all pairs of instructions. So we will essentially have order n square dependence detection as well as forwarding paths. This will become a massive bottleneck. So we'll also have complicated logic for detecting dependencies, for detecting hazards, forwarding. And to get the peak IPC, which is equal to n in an n issue pipeline, we need to ensure there are no stalls. Stalls will be there because of hazards. There will also be stalls because of taken branches. So we'll fetch a lot of instructions on the wrong path. All of them need to be nullified, cancelled. Furthermore, there will be other things that when we are creating, so if you just look at the diagram over here, essentially we'll be creating a bundle of 3 instructions, right? 1, 2, 3, and sending the entire bundle in parallel. It is good if they are independent. Otherwise, we need to have internal forwarding. We'll have a lot of internal forwarding paths, right, from here to here, here to here, here to here, lots and lots of paths, right? And also we need to have forwarding between instructions of the bundle. What can further make our life different is if we difficult is if we have load and store instructions. Because see, finding register dependencies is easy. Registers are named storage locations. So the decode and operand fetch units can easily figure out and detect register dependencies. However, they will find it very hard to detect dependencies across memory addresses, because memory addresses are never specified in the instruction, right? They need to be computed. The memory addresses are dynamically computed in the execute stage, and there it is possible that different new dependencies will kind of come up from nowhere. There can also be dependencies between instructions in the same bundle, right? The 3 instructions that proceed together. That will make life hard. So then also finding long sequences of instructions without dependencies or with very few dependencies is in a sense impractical. So that's the reason what Intel Pentium did is that they had 2 parallel pipes. More than that would have been impractical, and having 3 or 4 is clearly hard. So even with a multi-issue in-order pipeline, the best that we can do is get an IPC of 2. Most likely it will be much lower than this. So the gains, as we see, are not there. So what do? Well, we will have to change our thinking. So instead of processing in order, we should process out of order, which means that we will not observe or respect program order. All right. So this is out of order processing. It's called an out of order pipeline. So what does it mean to not follow program order? Well, what it means, so let me just take a little walk back into in-order. So in an in-order pipeline, what we said is that, look, we have a sequence of stages. and we have a sequence of dynamic instructions. A dynamic instruction has been defined before, so it's the instructions that a processor encounters. So they keep coming in, you keep executing them. Whenever you detect something has gone wrong, well, you stall. And as compared to, well, what was before this? Before this, we had a single cycle processor which did not have any pipelining, right? The entire thing happened in one cycle. It was one long cycle, right? One ultra long cycle. In this case, these are short cycles. So where was the advantage coming from pipelining? Well, it didn't come from IPC because the IPC reduces with pipelining. The advantage came because we could crank up the frequency and F max was proportional to K, right? So that's where the advantage came from. But then we found there are limits, and the main limits were that, look, finding independent instructions was hard, particularly when we considered parallel in-order pipelines. That's where finding independent instructions became difficult. And the main reason was that we are kind of being constrained by program order, right? So that is the main problem, that we cannot, even if there are independent instructions way down in the instruction stream, we can't pull them out and execute them, right? We'll have to proceed in program order, which would basically mean in this diagram, first execute this instruction, then this, then this, then this, and so on, which in a certain sense is not really fair. All right. So let us look at the structure of dependencies over here. So we see there are too many dependencies, but there is a certain pattern. So the pattern is that the first three instructions have a dependency of this kind, as you see, a read after write. Again, here another pattern, but between them, between this block and that block, well, they are independent. Does this give us an opportunity? Well, yes, it does. Let's move to the next slide. See, if I were to execute it on a two-issue out-of-order processor, right? Out-of-order will be given a triple O designation. If I were to do that, what I would do is that in the first cycle, I'll fetch this instruction and this instruction. Just go back. It is essentially this instruction and this. Fine, I can do that. In the next cycle, I can execute this. I don't have to, I don't need any stall cycles because I can forward the value of R1. Similarly, I can fetch and execute this. Again, stalling is not required, forwarding is good enough. Finally, I can get the last instruction. So since I have an issue width of 2, I'll also have a fetch width of 2, which means I can fetch two instructions, two independent instructions per cycle, decode them, and send them down to the execution units. So as you can see over here, we are executing two instructions in parallel. When we are doing that, it is true that they have dependencies, but still, since we are executing out of order, we can, without waiting for any, waiting for instructions before an instruction in program order to complete, we are breaking the order, extracting more parallelism, as you can see right here. And instead of taking 6 cycles, which we would have done in the previous example, with forwarding enabled, of course, we are doing it in 3 cycles, which of course is a fantastic speed up of 2 times. So this shows what we were discussing, that cycle 1, 2, and 3, and this is how we execute the instructions. All right, so just take a look at this diagram, take a look at this. So the advantage of an out-of-order processor is rather clear, that the execution is not as per the program order. Instead, it is as per the data dependence order, in the sense that the producer instruction always executes before the consumer. That's the only criterion that you have. Or in other words, the consumer is executed always after the producer. right? So that is the criterion that we have, that is the criterion that we will use, that the consumer will be executed after the producing instruction. So in this case, as we see, this is always happening. This is the producer, this is the consumer, the producer, consumer. So this is the data dependence order that we are following, and because of that we could extract more parallelism out of the program by executing our instructions out of program order, not in program order. So what's the basic principle? All right, so the basic principle is rather important. What we do is we create a pool of instructions. So basically we always fetch in program order, that's important. So we always fetch in program order, and then naturally if we have a execute bandwidth of, let's say, 4, our fetch bandwidth also has to be 4 to match it. So we will see it needs to be similar, but now let's assume that if the execute width is 4, issue width is 4, right? We are also fetching 4. Then we fetch instructions, put them in a large pool of instructions, right? In a large instruction pool. So the hardware term is the instruction window. So we'll use the term instruction window and pool kind of interchangeably. The next step is to find instructions that are mutually independent and whose operands are ready. So these are the two important criteria. The first is that I find a set of instructions to execute together. There should be no dependencies between them. That is criteria 1. That's very important, right? Because if there are dependencies between them, we can't forward. One has to wait for the other. And all their operands have to be ready such that they're ready to execute, right? These two are obvious. And then we execute them out of order. So this will give us the parallelism that we saw. And that was huge. I mean, as compared to a small improvement, this was giving us 2 to 3 times additional performance. So the key term that we are using here, we used it in the last slide as well, is ILP, instruction level parallelism, which is essentially the number of ready and independent. So ready meaning that the operands are ready, so inputs are ready, and independent instructions we can simultaneously execute in a cycle, right? This is ILP. So clearly some programs will have high ILP. Sometimes the programs may have low ILP, but the compilers can compile them in such a way that more ILP can be exposed. So it doesn't matter in whichever way. So we essentially extract the ILP, and on the basis of that we execute instructions in parallel. So here an example of a pool of instructions. We are revisiting what we had. These are all our instructions. So we want to, as we said, we issue ready and mutually independent instructions. So here we go, an animation follows. We first bring in 2 ready and independent instructions. Once R1 and R5 are computed, we again bring in 2 more. Again bring in 2 more. And in 3 cycles we are all done. Here is the greatness of out of order execution. So what is the most important factor? Well, it is to quickly build a large pool, because larger is the pool, the more instructions we will find to execute in parallel, right? So larger the pool, all right? Larger the pool, the more instructions we can execute in parallel. So more is the ILP that we can exploit. So how large should the pool be? Well, the pool is, we will treat pool more as a kind of a conceptual entity, and the hardware structure that stores this pool of instructions, we'll call it the instruction window, which is nothing but a simple queue of instructions. So the queue is filled in program order, but then of course you extract instructions from the instruction window in data dependent order, and then they are sent to the execution units, right? You have a set of functional units, adders, subtractors, dividers, multipliers, etc. So instructions from here go there. So the typical instruction window sizes range from 64 to 128 instructions. They need to be large. So because larger is the instruction window, the more independent and ready instructions we can find, right? The more instructions we can execute in parallel, higher will be the IPC. So the important question that we need to answer is, how do we create such a large pool of instructions? Because we will have branches in the code, right? So we need to ensure that the entire pool, the entire window, all the instructions are on the correct path. They are not on a wrong branch path, because typically we'll have an if statement which will have two directions. Again, one more if statement. So if we were to create an instruction pool, and let's say if this is the correct path, right? So we need to somehow guess the branch directions and fill instructions from the correct path. Because any branch, if you kind of get it wrong, right, then all the instructions after it will be in the wrong path. So the entire window is gone. So the entire window basically has to be populated with instructions from the correct path. That is very, 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 very important. So given this, let us take a look at a simple loop. So if you see a loop, as you can see, there are a lot of branches in here. We need to test if I is less than m, if j is less than I, if j is divisible by 2. So with all of these things, for such a loop like this, if we kind of unwind it, we will have a path like this. And for each of the branches, we need to somehow predict it correctly, because we would not have executed that many branches, right? And so to essentially fill a large window without executing the branches, we'll have to predict them and fill the window with instructions from the correct path with a very high probability. So how do we create such a large instruction pool? Well, the option of evaluating, so let's say that one in 5 instructions is a branch, and there are 100, we have a 100 entry sized instruction pool, then it will have 20 branches. So we clearly don't have the option of, picking out those 20 branches and evaluating them, because every branch would be dependent on a few instructions before it. It will be dependent on their result. So they also need to be executed. Similarly, another branch, it also needs to be executed. Essentially, all the instructions that determine the outcome of the branch, all of them need to be executed. So for us to actually pre-execute these 20 with high priority is not an option. So just in case it crossed your mind, let's say pre-execute branches, give them ultra high priority. This is not an option, because there will be many other instructions that determine the the outcome of the branch. So this is not a feasible strategy of filling up the window, because we'll end up executing the program. Our aim was to somehow fill up the window, then find independent instructions from there quickly and execute as many as we can. So given that this is not an option, the only option we are left with is to somehow predict the directions of the branches and the targets. So given a branch, so let's say DEQ, so it has two attributes. One is the direction of the branch. Is it taken, not taken? The other is the target of the branch. So the target of the branch is where the branch points to. Even that needs to be predicted because that has to be computed and we don't have enough time. So we want to predict as much as we can in terms of the direction and target and fetch instructions. Let us now retrace our journey. So we said that we need high IPC because, well, reducing the number of instructions and also increasing the frequency seem to be difficult goals. So some amount of saturation we had already reached. For high IPC, we need to exploit a large amount of instruction level parallelism. Hence, we need a large instruction window such that we can find a lot of ready and independent instructions in one cycle. But because to sustain a large instruction window, let's say an instruction window has 100 entries, it will have roughly 20 branches. Those 20 branches we cannot execute, we don't have the time for executing them, right? Because I mean the branches are never executed independently. Branches are the outcome of a branch is determined by a large number of instructions before they have to be executed. So clearly we cannot fill up a window that quickly by executing branches. That's not practical. We will have to predict branches, both their outcome as well as their target. And all of these branches, we need to predict all of the branches. As I said, prediction involves two things, outcome and target. Outcome, we can say outcome or direction, so it's taken, not taken, and the target, right? Direction, so you can say direction slash outcome plus target. So note that if there are 20 branches, all 20 of these branches, all of these branches have to be predicted correctly to fill the entire window with 100 correct instructions. Even if one of these branches is predicted incorrectly, the entire pool of instructions is pretty much useless, or at least still that branch and all the instructions fetched after it, they are useless. So as far as we are concerned, it's a problem even if there is a single misprediction, because a large part of it will become large part of the pool, even if we treat it as a queue, will pretty much become useless, and we will have to remove them and again refetch. That will cause a major issue. So we want our ideally speaking, we want our entire pool to be correct. Consider the maths of branch prediction. So let us say that we have n instructions. So on an average, n instructions will have n by 5 branches. So let's assume that the number of branches is n over 5, n by 5. So let the probability of predicting any given branch incorrectly, wrongly, be p. And let's assume is the same for all branches, right? The probability of making a mistake is p for a given branch. So the probability of predicting all the branches correctly. So what is the probability of predicting a single branch correctly? Well, it is 1 minus p. The probability of predicting all of them correctly is 1 minus p, given the fact that they are independent events, right? We are assuming that they are independent events. Okay. So the probability of predicting all of them correctly is 1 minus p times 1 minus p times 1 minus p. How many times? N by 5 times. All right. So this makes it 1 minus p to the power n by 5. So probability of making at least a single mistake, a single branch misprediction in this full pool of n instructions, right? Of making a single mistake, 1, 2, 3, 4, 5 doesn't matter, but at least a single mistake is 1 minus this number, which is 1 minus p to the power n by 5, and let this value be Pn, which is of course has to be a function of n. All right. So what is P? P is the probability of mispredicting a single branch, and Pn is probability of making a single mistake, a single branch misprediction in the entire pool, which means that with this probability the entire pool needs to be jumped. So if I were to just plot a probability of Pn versus P, and of course, in this case, P is in percentage, both are in percentage, right? So essentially a probability of 0.01 would become 1%. So as you can see, if 90% of the time I want my window to be all correct, which means my Pn is equal to 10%, that's the number of mistakes that I'm allowed to do, right? That's the number of times I'm allowed to have a window with at least one mispredicted branch. So if I were to bound Pn so by 10%, and I look at the corresponding point on the curve, so this is roughly 0.5%, slightly more, maybe 0.55%. And so I've approximated it to 0.5, might not be a very accurate one, but 0.55, let's say. Doesn't matter, but we can say that roughly the probability of mispredicting a single branch has to be in the ballpark of this figure, which means that a successful prediction probability of any given branch has to be 99.5%, which is huge. Predicting anything with such a massive accuracy is clearly going to be a very hard task. And this is something that we have seen, the math from here, if I were to just plot it over here. So what am I doing? I'm essentially plotting Pn with small p. If I were to do that, and the x-axis represents the probability of making a mistake with any given branch, and Pn is the probability of the entire window getting junked. So if let's say, and when will the entire window get junked? If there is at least a single mistake, because then we know that not everything is correct, right? And so if we were to do that, then we see, even if let's say I say that look, 80% of the time I want my window to be all correct, and I draw here, still if I were to see, well, this is probably 1.1%. So even here also 98.9% of the time, your per branch prediction accuracy has to be 98.9%, which is very high, which means that the branch prediction error rate, misprediction rate, has to be extremely low. This means that if we want to sustain a large instruction window, this automatically implies that we need a very, very low. I'm deliberately adding two varies to emphasize the fact that the branch prediction has to be extremely accurate, a very, very low misprediction rate. If it is not the case, then we can quickly see that we will have disaster at our hands. So let's say instead of 0.5 is 2.5%. So well, even 2.5% error is not bad. It's 97.5% of the time correct. So here also, as you can see, we would end up with a roughly 40% error rate for the window, which means that 60% of the time the entire window will be correct. 40% of the time there will at least be one misprediction in the window. So pretty much we can't trust the contents of the window. So a 60-40 ratio is still quite bad, because as we will see when we design the pipeline, having a wrong branch in the window is a very, very expensive thing in terms of time. So we typically don't junk the entire window. We try to kind of save all the branches before all the instructions before the mispredicted branch, before it in program order. But nevertheless, it does have a very substantial performance penalty. And as a result, getting a correct window is very, very important, right? And we are talking of extremely low misprediction rates, extremely high prediction accuracies, and extremely low is of the range of 0.51, 1.5%, 2%, which means that we need to be 98 to ideal branch predictor for a single branch. Its accuracy should be in the range of 98 to 99% to sustain a window of 100. This automatically places a limit on the instruction window size. It cannot be more. If it's, let's say, 1000, then this number will get very, very close to 100%. We can never design such an accurate predictor in practice. So it is far better that we stick with what we have, and a practical window size is thus limited to maybe 150 instructions maximum, not more than that, primarily because the branch predictor's accuracy is limited. So what did we just learn? That look, if we need a large instruction window, we need a very accurate branch predictor. And there is something that you can study there in information theory. There is a result called the Fano's inequality, which says that look, there are theoretical limits to predicting a given sequence. So in this case, a sequence of branches, and this has to do with information content of the stream. So given the fact that we run into theoretical limits, our branch predictor also has a hard limit on its prediction accuracy. So this limits the size of the instruction window, and we can't go more than that. It's not practical to go beyond that. So now we will take a turn towards analyzing. So now, where are we? We are at the point where we have realized that out of order execution is required, that we have kind of convinced ourselves. Then for out of order execution, we need a large instruction window, which is a large conceptual pool of instructions. From this, we pull out ready and independent instructions. To create a large instruction window where all the instructions are preferably on the correct path, we need a very accurate branch predictor, where the branch predictor is predicting both the target as well as the outcome. And we are talking of extremely high accuracies over here, as we just saw from our mathematical analysis, 98 to 99%. And with that, we can fill our window, we can execute. Have we solved all the problems? We haven't, because in an out of order pipeline, we'll be looking at many more kinds of dependencies other than the simple raw dependencies, RAW, read after write dependencies that we have seen in the in-order pipeline. So we will handle the nature of dependencies in the next lecture of this lecture series.